Plastic. Could you function without it? I know I couldn't. Hello, I'm Ashvin Tharumanathan, and today I'll be examining polyethylene, one of the most commonly used plastics around. Polyethylene is extremely versatile and can be used for just about anything. More personally, however, it affects my daily life through my spectacles, which I use to see, and cling wrap, which I use to pack my lunches. Polyethylene is created through the polymerization of ethylene, which has 2 carbon atoms and 4 hydrogen atoms. Carbon atoms have 4 valence electrons, meaning it can form 4 bonds. In the polymerization process, this double bond here is broken to allow additional single bonds to form amongst the carbon atoms, as you can see here. This is known as polyethylene, and it is an alkene. The electronegativity of carbon is 2.55 and hydrogen is 2.20. This gives a difference of 0.35. As such, polyethylene can be said to be a non-polar molecule. That is, the electrons are shared equally. Non-polar molecules are affected by a weak transient intermolecular force known as van der Waals force. There are many types of polyethylene, but today I'll be focusing on low-density polyethylene and high-density polyethylene. The physical properties of polyethylene are heavily influenced by its density. Now, the density of polyethylene depends on the extent and type of branching present in the material. Low-density polyethylene has more branches than high-density polyethylene. The amount of side branching varies the closeness that the molecules can come together. As low-density polyethylene chains have a lot more branches, they don't fit very well together. This results in a weaker intermolecular force, as the instantaneous dipole-induced dipole attraction is less. The weak intermolecular forces between the carbon chains are what allows it to fold, bend, and stretch easily. This is what makes it ideal for cling wrap. The induced dipole forces increase as branching decreases and molecular size increases. High-density polyethylene is more linear and can be packed closer together, which produces a stronger interchain attraction and, correspondingly, increases mechanical strength. Branching also affects crystallinity of the molecule, which is very important. Crystallinity implies that the subunits used to make up the substance are arranged in a regular organized array. Low-density polyethylene has low crystallinity, as the main chains have many side chains that lead to random irregular packing, such as here. As such, it is an amorphous structure. Now, this is significant in the production of lenses, as it makes the plastic transparent and allows me to see through them. To summarize, polyethylene's density affects its physical properties. The density, in turn, is controlled by the extent and type of branching. More branching leads to weaker intermolecular forces, lower crystallinity, but this results in higher flexibility and transparency. The more linear it is, the more rigid it is due to the stronger intermolecular forces. Now, these are just some of the reasons for plastic's versatility.